All right, so as we saw when we're talking about strong acids or bases, it's relatively straightforward because they completely ionize. However, when we're talking about weak acids, it gets more complicated, and that's because weak acids can vary in strength, right? Some weak acids are stronger than other weak acids, and some weak acids are weaker than other weak acids, right? Weak just means that they do not completely ionize. So let's take a look at what these would do. So we have HA here. This is just a generic acid, right? Where A is some kind of other component, right? And then the H represents the acidic proton. And then we combine that with some water. That's a liquid. And then the acid is going to donate this H plus to form our H3O plus, which is the same thing as just writing H plus. And then we have A minus, which is then the conjugate base of HA. And so we see here, the arrow here is an equilibrium arrow. And so if we're thinking about equilibrium, we can write a K, right? Remember, K is the products taken to their coefficients over the reactants taken to their coefficients. And so this gets a special K as well. So this is called Ka because the A stands for acid. And really it's called the acid ionization constant. Or the Ka of this acid, right? And so it's products over reactants. So our products here are H plus or H3O plus, and then the conjugate base, A minus, divided by the original acid, right? HA. We don't include water because it's a liquid. And so we can say certain things about K. So as Ka gets bigger, right? If you have a bigger Ka, that means that you have more products. And in this case, the products are H plus, right? So your amount of H plus you have increases. And since an acid is defined as how much H plus you give, that means that you're a stronger acid, right? So the bigger the value of your Ka, the stronger of an acid you are. In terms of kind of a strong acid, the concentration of HA at equilibrium will be equal to 0 because it's completely ionized. And so your Ka actually goes towards infinity. And we'll talk about how you measure Kas or Kas for stronger acids later on. However, you have to understand the concepts of Kas, and sometimes Kas will be given. But more often than not, when we're talking about the strengths of acids, what we're talking about is pKas. So you'll hear the word pKa used a lot more often than Ka. And remember that P just means negative log. So the pKa is just going to be the negative log of the Ka. And so we really got to know this relationship here. As the Ka gets bigger, right, just like pH, right, what's going to happen to pKa? Well, it's actually going to go down, right? And then both of these mean a stronger acid. So for a stronger acid, you want a high Ka or a low pKa. So let's take a look at some examples real quick. So I'll ask which one of these two is the stronger acid. So for the first problem, we'll say the Ka of 1.0 times 10 to the negative 4 or 1.0 times 10 to the negative 6. For this one, we'll say a pKa of 1 or 3. And then for the last one, we'll say a Ka of 1.0 times 10 to the negative 5 or a pKa of 4. Right? So for each one of these three problems, circle which one of these is the stronger acid. You want to go ahead, pause the video, and work this out yourself. All right, so hopefully you pause the video and work this out for yourself. We learned Ka, the bigger the Ka, more products, stronger acid, right? So 1.0 times 10 to the negative 4 is a bigger number than 1.0 times 10 to the negative 6. So this acid is stronger. Next up, we have a pKa of 1 or 3. Remember, pKa is the opposite. Smaller pKa is a stronger acid, similar to how pH, when we go down, we get more acidic. And so the acid with a pKa of 1 is stronger than the acid with a pKa of 3. And then finally, we have a Ka of 1 times 10 to the negative 5 or a pKa of 4. So we have to change one of these. I like to think of things in terms of pKa. So we can just take the negative log of 1.0 times 10 to the negative 5, and that will give our pKa, right? Our pKa. And so if you do the math here, you can also just tell from the exponent, right? It's going to be 5, right? So a pKa of 5 or 4, the lower pKa is a stronger acid. So the pKa of 4 is the stronger acid. And so similar to kind of pH and pOH, like a Ka will equal to 10 to the negative of the pKa. And then let's see, I have this little picture. Shows varying acid strengths and varying values of Ka. So what we have here is just a bunch of various different acids, and then you have their Ka values and then their pKa values. So generally here, as we go up this table, we get a stronger acid. Except for these two. These two are flipped for some reason. I don't know why. They organized this table in terms of strength, but then didn't flip these two, I guess. I don't know. And so you can tell the relationship between the Ka and the pKa, right? Here the pKa is, or the Ka is very small. Here the Ka is much bigger, and the bigger Ka is a stronger acid. Here the pKa is higher. Here the pKa is lower, and the lower one is the stronger acid. And you can tell kind of 10 to the negative 10, the pKa is approximately 10. 10 to the negative 8, the pKa is approximately 8. 10 to the negative 5, the pKa is approximately 5, right? Negative 4, approximately 4. Negative 2, approximately 2. So go ahead, just pause the video, look at these acids, make sure you're comfortable with them. They have the Lewis structures as well. You see this OH is a common motif, especially when you also have this doubly bound oxygen with it. But there are other things you can see here, right? HF, HCN, that kind of thing.